So okay, then I would like to. So let's probably smoothly start the seminar. So it's already 3 minutes to 11. So greetings, dear colleagues. Today we have our next optical seminar. So before we start, I would like to remind you the few rules. We ask you to hold your microphones switched off. You will be able to switch your microphone on when you would like to ask the question. And there are two ways to ask a question, preferred ways to ask a question. You can either raise your hand and we will interrupt the speaker at the most appropriate moment. Or you may also type your question to the chat, we will read it at some point. Today I'm very happy to introduce and to welcome Professor Isabelle Staude from Institute of Solid State Physics, Friedrich-Schiller-University Jena. The talk is devoted to active dielectric metasurfaces for light field control. Isabelle, please.
Yeah, thanks a lot, Anton, for introduction and also for the invitation. So it's a great pleasure to be here, even if it's only virtually. Yeah. I'm really looking forward to this interaction and also listening to good questions from your side. Yeah. So as you saw, my topic is active dielectric metasurfaces for light field control. Anton asked me if I could concentrate a bit on like systems incorporating 2D materials. So that's what I did. So most of the talk, I will illustrate basically these ideas for active metasurfaces by discussing systems where active metasurfaces were realized using 2D materials, and only in the end there's a small part on a different kind of system, but we will see if we even get there. Yeah. All right. So yeah. I don't want to forget to mention this, so I mentioned it directly in the beginning. Of course, what I show is a team effort. So yeah, all the works that are shown were not just done by me or my group, but by several groups. And in particular for the 2D materials, I should acknowledge the group of Andrei Tochanin, who is also in Jena and growing these 2D materials by chemical vapor deposition. But also there's intense interaction with the groups of Falk Eilenberger, Frank Setzfand, and Thomas Perch. And then we also collaborate with Australian National University, in particular with Dragomir's group. And for the last part, which will not be on 2D materials, if I come there, this is together with Alexander Muravsky's group from Belarus. All right, so the outline of my talk is, there will be some motivational introduction. Maybe some of you who have, who had already quite a lot of interaction with me, maybe know this part. So I will introduce a bit more generally the all-dielectric metasurfaces that we are investigating, but I will try to keep it relatively short. And then we will look at different kinds of active metasurfaces. First, light-emitting metasurfaces, nonlinear metasurfaces. We will have ultra-thin optical metasurfaces. I think they don't really qualify as active, but I think it's also interesting in this context of 2D materials. And in the end, I would, if time allows, I would also show a little bit on tunable metasurfaces. All right, so all of you have seen images like this probably. So this is sort of a cartoon of what a metasurface is. So it's a sheet of nanoscale thickness here oriented out of the plane of your screen. And then we come in with a known input light field, and the metasurface transforms this into an output light field with some desired properties, which can be wavefront, polarization, spectrum, and so on. So how does the metasurface do this? It's basically a two-dimensional sub-wavelength arrangement of designed nanoscale scatterers, that interact with this known input light field in a desired way. And typically it can be a spatially inhomogeneous arrangement to locally control, control the properties. So we can approach this idea of the metasurface from two sides. Either we can consider an 3D optical metamaterial, which has been researched or has been a topic of research for quite a bit longer. And there it was, in this research area of metamaterials, like a decade ago or so, people were concerned all about creating effective properties by the designed arrangement of these building blocks, so that in order to create materials with optical properties that are not available in nature. Now you can see the metasurface basically as something like the 2D material counterpart of a metamaterial. So typically just a single or maybe two layers of such designed building blocks. And I should also mention that for metasurfaces, typically we are not so much concerned with creating some effective optical response, but it's more really about the functionality. Yeah, and the other side, we can approach the metasurface concept from, which is also very useful in the context of active metasurfaces, is to consider them as a 2D array of nano antennas. So a nano antenna is basically an efficient link between localized optical near fields and propagating light waves. And yeah, by then tailoring this antenna interaction, for instance, yeah, here I show this idea of this, yeah, this transmitting nano antenna where a nanometer is coupled, and then the nano antenna, yeah, extracts the energy from it and emits it to the far field in a desired pattern polarization and so on. Yeah, and the metasurface in this picture could be like a 2D array of such designed nano antennas. Yeah, so optical metasurfaces have been quite prominent in the literature in the last decade or so. And yeah, the main focus was really on this topic of, yeah, wavefront manipulations. And this is possible because such a metasurface can impose a position dependent phase shift onto an incident light field. There's this very simple cartoon. So if I, for instance, have here a metasurface, again, oriented out of the plane of the screen, then yeah, I can, for instance, in a very simple example, just design the scatterers such that they impose a linear phase gradient onto the incident light field, and this would lead then to a deflection of this light field. But of course, more complex things can be done. I show here two examples from other groups, like the Pharaon group and the Capasso group, who are very active in the area of metasurfaces. And you see that, like for instance, holographic metasurfaces or, yeah, lenses, metasurface lenses can be designed based on this concept. Now, I also chose these two examples to illustrate a bit that there are different ways, like how these nanoscale building blocks forming the metasurface can work or function. So there are different ways how this position dependent phase shift can be implemented. For instance, here for this Pharaon work, they have these little upright standing waveguides, and the cross section of the waveguides then locally, yeah, influence or like determines the group velocity in the waveguide and thereby the phase delay. And here is this idea of the propagate of the Pancharath-Namberi geometrical phase that is used for imposing the phase shift. So in our work, or what I should also mention, like in the whole community, I think most people are now agreeing that, yeah, that making metasurface out of dielectric or semiconductor materials, this is really the way to go, because the efficiencies can be much higher than for plasmonics. And yeah, we share this view. And in our case, what we use typically as building blocks of the metasurfaces are high index all-dielectric nanoparticles. So yeah, such nanoparticles can support a series of electric and magnetic multipolar modes. For spherical particles, these can be described by me theory. And here I show, yeah, the schematics of the two lowest order modes. Yeah, you know this very well in St. Petersburg. Yeah, so there's this electric dipole mode characterized by a linear displacement current, which scatters like an electric dipole. And here on the right-hand side, the probably more interesting magnetic dipole mode, which is characterized by this circular displacement current, yeah, and scatters then like a magnetic dipole. So we have, and there's also a series of higher order modes. So we have many opportunities to interact with both components of light field. We can get very careful control, and by now shaping the size, shape, and material composition and arrangement of these nanoparticles, we really have many options to tailor the interaction of light with these kind of structures towards specific effects or applications. All right, so I already mentioned the tailoring of the shapes. So being experimentalists, we are not so keen about spheres. They're a bit hard to make and control. So we like these extruded geometries like disks that we can make using electron beam lithography and reactive ion etching. Then if you look at the transmittance, for instance, of such a silicon nanodisk metasurface, you find these pronounced minima in the spectrum. And yeah, then typically what one does is perform numerical simulations, trying to get the best possible match, and also looking at the near fields and analyzing what these modes are that we see there, these minima. And here we see now nicely that they correspond to this electric and magnetic dipole mode in the structure. And here, for instance, this magnetic dipole mode, we really see this circulating electric field, yeah, which characterizes this magnetic dipole mode. If we want to be more sure, like not just look at mode profiles, one can also perform multipole analysis, for instance, to get really idea of the multipolar content in these modes. So yeah, this was yeah, I should just show this. There may be some people who haven't seen it. So this is now quite useful. If we have these disks, we have actually also, there's an advantage towards the sphere that we now have two geometrical parameters that we can tailor, the height and the diameter. So what I show here is experimentally measured transmittance and reflectance data, where we tune the diameter of the disks at constant disk height. And what you see is that we can now tune there are these electric and magnetic resonances. So the level of transmittance reflectance are color coded in these images. So here are these two resonances that you already saw in the previous slide. And now if we decrease the diameter at constant height, we can move them closer together, move them in spectral overlap, and yeah, beyond even. And yeah, so that's good. We have now the way to tailor these modes, but also like in this overlap region here, this is probably the most interesting because you see the structure gets more transparent. And this is not like a bad sample or so where we have lost the resonance, but this is really something that we can, yeah, that we can cultivate also in numerics, optimize it, and really find structures which have close to unity transmittance, basically. While the strong resonant response of this system, this mi-resonant response, this shows in the phase where a 0 to 2 pi phase variation is seen as the wavelength is swept over the width of the resonances. And yeah, this is quite useful because like a single resonance would only give you a pi phase jump, right? Not 2 pi. So we can also make an analytical model, modeling each of the disks as a coupled electric and magnetic dipole. And then in such an ideal scenario, we can even show that such a, we call it Huygens, dielectric Huygens metasurface can have close to unity, or like ideally unity transmittance, and shows really this phase shift of 2 pi. Excuse me. So this is now quite useful for waveform control because it means we can manipulate the phase of the light wave at will with full phase coverage of 2 pi while maintaining high, ideally unity transmittance. And this is what you want. Typically you don't want to reflect much of your light. You don't want to absorb it. You really want to transmit it and manipulate it in the desired way. So yeah, we used this kind of concept in order to demonstrate a few functional meta devices. The first one was a very simple one, just this Gaussian vortex beam shaper. Here we varied the lattice constant of these disks in order to implement a 0 to 2 pi azimuthal phase variation. And here you see the retrieved phase of the near IR vortex beam that was generated. So this worked. A bit later, we also tried our first hologram. It's like a small hologram. Here you see the light microscope image again of the whole metasurface. Here these brownish and greenish areas again correspond to different lattice constants of silicon nanodisks. But now as you shine the near infrared laser on this, it creates these letters H nu behind the metasurface. And more recently, together with Frank Setzfand's group, we also did such a metasurface mask which creates a helical point spread function. So basically here's a cut through this. You see these 2 points, and if you move now the z coordinate, the orientation of these 2 points will basically change in order to form a helix. And if you image such a scene through that, in combination with image processing algorithms, you can retrieve basically depth information from the image, which is shown here. So yeah, there are a few nice applications where this also works well. They have a few nice properties, like the efficiencies are way over 80% now. They are like, the structures are typically very flat, and also quite robust because it's just and CMOS compatible because it's just silicon on glass. However, at this point, you may want to challenge me also and say, well, but you showed yourself also there are many ways of creating such wavefront shaping metasurfaces or wavefront shaping devices from a nanostructured thin film. So why should we care now about your Huygens metasurfaces? And so for this, let me take a little detour. So I was recently at some industry meeting, and after my talk, I showed a little overview of what we were doing there. And a lady from the company raised her hand and said like, okay, that's nice. So which surfaces of our smartphones would you want to replace now by your metasurfaces? And this was quite a practical question for me as a fundamental scientist, but it made me think a bit. And it's actually like with these passive wavefront shaping devices, I'm not so sure like where like you really have to find niche applications. I'm not sure if they will make it into the smartphone. Yeah, so of course it sounds very attractive to have a flatter lens, because the lens is still what sticks out of most smartphones. Yeah, if they are flat, the lens is still a bit thicker, so they would like something flat. But also these, like, this is even not the newest generation, as you may see, so often they have now many cameras and so on. Yeah, but like really competing with the technology that's already there is very difficult, yeah, with these kind of metasurfaces. So I sort of thought of a joke that we could use some yeah, like photonic color to make the nice housing and so on. But well, I don't think this is what funding agencies will pay us for to do research so much. Yeah. So what I really think is the key where we can move with this field is towards tunable light emitting and nonlinear metasurface. So really these active metasurfaces, because if we go in this direction, then there's so much more opportunities. One could, for instance, work also on screens, on projectors, on communication, even quantum maybe. Like there are so many opportunities then that one could think of, which may even, some of them may even make it into the smartphone on the long run. All right, so, and yeah, yes.
We have a couple of questions before.
Okay, yes, please.
So the first one was from George Zograf.
Yeah, Professor Staude, thanks a lot. So I have a pretty naive question regarding the previous slide. So yeah, this in the top right corner, there's like a work. It was done probably like 5 or 6 years ago. I wonder how in those days people were predicting the final image, since right now I'm quite sure that people are using like machine learning or some other computer related things, and at that time what was like the approach to predict what was the final picture of hologram or something like that?
I mean, there's so how we design this or how we do it is first, I mean, you have to do 2 design tasks. One is to find the phase mask that is suitable in like to create the desired image. Yeah, so this is a problem which was addressed far before we used metasurfaces for that. Yeah, so there's typically this Gershbeck-Saxton, or so-called IFTO algorithm, that is used to do this. Yeah, so, and we use this as well, and I think it's also like, even now there's no need to, it's an inverse problem, but I don't think you would call this machine learning. Yeah, it's just a well-known algorithm that you can use, and it works well. Yeah, so we're still using that. And then the second design challenge is, if you know your ideal phase mask, you sort of have to transfer it into a metasurface design. Yeah, and so for this, like typically we have like a pixelated version then of this phase mask that we want to implement. It's also, again, just by forward propagation through this, you can determine how the pixelation affects now your final image. But the bigger challenge is then to find also the metasurface geometry that you have to implement locally in order to really get this phase mask in the end. And for this, like in many cases, we did it just using parameter sweeps. Yeah, so, and it's also, because we don't have that many parameters, it's actually quite feasible. So in this case, we sort of we're fixed to this Huygens regime, which fixes the aspect ratio of the disks. Yeah, and the operation wavelengths basically fixes then the overall size of the disks, and then all we had to sweep was basically the lattice constant. So there was no need to use any any advanced machine learning for that. Of course, if you want to go to more complex systems, implement more degrees of freedom, somehow use them and so on, then like as soon as you get more than 2 parameters that you want to adjust, then I guess it's cool to go to like more complicated algorithms. But here, this is how we did it, and I have to say we also use this kind of design still a lot. Yeah, so if it gets more complicated, it's not necessarily immediately machine learning that we have to use. Often, like if we want to automate some design task, often like a simple gradient descent optimizer works beautifully. Yeah, so I think it really scales with the complexity of the problem. And if we have like 2-3 parameters, we are still quite good with more classical algorithms. But I agree, the trend goes there, and there may be also problems which where it's very difficult to get reasonable results then without such advanced algorithms.
Yeah, many thanks. Thank you very much.
Okay, and we have another question from Ivan Toftel, Vanya.
Hello, Isabelle. So can you say a bit more on three-dimensional imaging? So it wasn't really clear for me. And
Okay, no worries.
if you have, for example, a reflection on the image, how does it processes or?
Yeah, so I didn't put so many details here, yeah. So because you can, as you can, it was more like for illustration of the concept. So yeah. So I don't have much more image material that I can show at the moment, yeah. But maybe I can try to explain again. So it's basically a phase mask. It's relatively large. It uses the same kind of metasurface principle that we used here at the top. So basically a Huygens metasurface where the main parameter that was tweaked was the lattice constant again to implement locally the phase values that are needed to create a helical point spread function. Yeah, you can imagine this like the double helix of the DNA. Yeah, and the two strings of this DNA. This is where your light will be concentrated. So as you progress through, like that, this is a cut here through the point spread function that you see here on the left hand side. If you would move now on in y direction, this orientation changes of the 2 points. Yeah, and you can imagine if you if this is what hits your object, yeah, then this will cause different distortions to the image in different positions. Yeah, so the image itself, I think it's shown in the paper, it looks quite blurry. Yeah, that's why also this depth information is not super sharp. Yeah, because this, of course, this helical point spread function blurs the image a bit, but I would say like the local blur depends then on the local orientation of these two spots that you see, and this depends on depth.
Okay,
so
I think I got the
artifacts that you have locally, you can then extract depth information, but I'm also not an expert on these algorithms that are used for this. Yeah, so there was a local expert from Jena who really works on this and who could provide the algorithm to really take the image and get the depths from it. Yeah. Does it answer your question? Okay.
Yes, it is.
Okay, that's it for now.
Okay, then I will move on. Yeah, so we had the smartphone. So yeah, so I was trying to make the point that for active metasurfaces, there's much more potential, yeah, like application potential. And the next thing I want to stress is that with these resonant metasurfaces that I introduced now, we really are in a good position to make active metasurfaces. And the reason for this is that on the one hand, yeah, because these are resonant and basically their function is based on the excitation of these well-defined resonances in the structure. Yeah, on the one hand, we have this strong spatial and spectral dispersion. This means we have the opportunity to tailor frequency and angular sensitive optical responses. Also, it facilitates tuning and switching. If you imagine you have a strong dispersion, like spectral dispersion, like maybe a sharp peak, and you're able to tune this a little bit by changing something in the system, then at a given wavelength point, this small, like even a small tuning will lead to quite a strong tuning contrast. Yeah, so this is good to be dispersive here. And also yeah, now we come back to this image of the metasurface as an array of resonant nano antennas. So because each of these little building blocks in the resonant nano antenna acts like a little antenna and can locally enhance the electromagnetic near fields and thereby also enhance light matter interactions. And we can use this to enhance nonlinear optical effects, for instance, spontaneous emission, any other light matter interaction effect you can think of. So there's probably still room for research. And yeah, so now I will concentrate basically on these topics of spontaneous emission, nonlinear optical effects, and probably a little bit of tuning switching in the end, and yeah, discuss these active metasurfaces, light emitting, nonlinear, and tunable. All right, so yeah, so if we talk about active metasurfaces, like a plain silicon metasurface on a glass substrate is yeah, can be used in some cases, yeah. So there will be maybe some autofluorescence from this that we can study, and silicon also has a nice nonlinear optical response, but only third order because it's an inversion symmetric, has an inversion symmetric crystal structure. So yeah, so it's limited what you can do with just such a passive metasurface, and to really add additional functionality, like it's typically what we have to do is to integrate some active components in the metasurface architecture, and 2D materials are very interesting candidate for this. So in particular, when I talk about 2D materials, in most parts of this talk, these will be monolayers of of transition metal dichroic coordinates, something like MOS2 and so on, like materials of this family. And they are particularly interesting because if thinned down to the monolayer, they show a strong direct bandgap photoluminescence. They also show spin valley coupling effects. So, and for us, it's particularly interesting because this allows for chiral photoluminescence emission, which is very interesting to couple to nanostructures. And like from application point of view, people like to use this spin valley coupling for so-called valleytronics. So basically, you have these equivalent K and K prime valleys in these materials where excitons can be located. And because they are inequivalent because of the lack of inversion symmetry in these monolayers, this can be basically used as a as an information carrier, like which valley this exciton sits in can be something like a logical 1 or 0, for instance. And so this field of valleytronics, and there I think that nanostructures and metasurface could be very good candidates for locally preparing, addressing, and manipulating such valleytronic states. So then these monolayers also provide a strong second order nonlinear response, again, because they have a non-inversion symmetric crystal structure. And finally, they can be tuned. So using electrical gating, both photoluminescence and second harmonic generation can be tuned quite efficiently in these materials. So you see, we have all these points of light emission, nonlinearity, and tuning that these materials can provide us with. And on top of that, the two-dimensional nature of these TMDs is also ideal for integration with metasurfaces. So it's basically like putting a slice of cheese on a bread. Here it's a double layer, and but you can. I mean, this is only like the conceptual image. Yeah? So the monolayer would be a very much thinner slice of cheese because it's just like compared to the thickness of the metasurface, because it's really just below 1 nanometer thick, whereas the metasurface is typically on the order of 100 or a bit more nanometers thick. Then the idea is basically to use now metasurface to enhance the interaction with these ultra-thin materials by subwavelength light concentration, and the 2D materials to use them as active light-emitting nonlinear tunable components to enhance the scope of our metasurfaces beyond passive wavefront shaping components. So I will start now with this concept of light emitting metasurfaces. I've showed this cartoon here before, and for the light emitting metasurfaces, the idea is now basically to get rid of this known input light field and consider the metasurface itself as a flat source of tailored light fields. And for this, we consider the metasurface as an array of resonant dielectric nanoantennas that are driven by localized sources. So the challenge is to integrate the nano emitters into the metasurface architecture, and using like hybridizing them with 2D materials. I will show that this is a way to do this. So what can we expect now from the metasurface to do with the emission from the 2D material? So here I show the measured fluorescence count rate from a metasurface just with a single emitter placed on the position REM on it. If you have an ensemble of emitters, it's really hard to describe this analytically. So, but it's still useful to consider this for a single emitter. Just to get an idea of the physical processes that take place in this hybrid structure. So so what we have is several factors. So one is this excitation enhancement. So typically we still pump our structures with some excitation lasers. On the long run, if you think of devices, this will probably be replaced by some electrical pumping. So, but still in this optical, for optical pumping, we have to take into account that there may be excitation enhancement happening, although for most structures I show this is not so severe because the structures at the excitation wavelengths, they are typically already absorbing quite a lot and there are no pronounced resonances. Then we have the quantum yield enhancement. So this is basically Purcell effect, which can enhance the decay rate and thereby the quantum yield of the 2D material or of the emitter in this concept here. there's this extraction efficiency, just how much light we get out really now of this metasurface slab, and also the collection efficiency. So this is something like typically you need some kind of optics to collect the light that you're generating, and this certainly, yeah, this typically has a certain NA, like numerical aperture. So if you manage to sort of direct the light more efficiently towards the detector and collect it, then this is yeah, this can also enhance the measured fluorescence count rate. So if we use dielectric building blocks, then what we can expect are typically moderate quantum yield enhancements, yeah, unless we go to really high Q metasurfaces, but this is not what I'm showing here most of the time, and but preserving a high radiation efficiency because the losses in the structures are pretty low. So what the metasurface can also do, apart from, yeah, acting on the count rate, is to directionally shape the emission. And yeah, so this factors then into this collection efficiency also. So, and how can it do this? So on the one hand, we have the effect of the array or arrangement. In plasmonics, this was quite intensely studied. Here I show this work by Lozano et al. From 2014, where just this was like an array of plasmonic nanodots. And then you could see this is, I will show quite a lot of these backfocal plane images, also like backfocal plane imaging of emission pictures. So what you see here is basically the Fourier plane of the emission of the collection objective. So each point in this image corresponds to a direction of emission. Yeah, so the center, for instance, would be emission normally out of the plane of the metasurface. And yeah, so here you see now how such an so how this emission pattern can be shaped by the arrangement already for these simple plasmonic structures. But then we can also have an antenna effect from the individual meta atom, in particular for these structures that support several multipolar orders. Yeah, it can be shown, for instance, that superimposing a quadrupole and a dipole, one can already from a single particle get quite a directional antenna. And so for shaping emission patterns, we have both the form factor and the structure or array factor available, yeah, to do this. So there are many degrees of freedom now to tailor directional properties in metasurfaces. So first work we did here was to basically put MOS2 flakes onto, yeah, on top of a resonant silicon metasurface. So there's a schematic of this. We use in this work such CVD grown monolayers by Andrei Trochanin. So they do this growth, and yeah, so this is how they look like as grown. And then we perform a wet transfer procedure. And this is Tobias, who was the main person in this work, yeah, PhD student in my group. And yeah, then we end up with these hybrid structures. So the metasurface looked something like this here on the left-hand side. There's a focused ion beam cut through the assembled structure, yeah. So the MOS2 basically sits on top of these silicon nano antennas, and here is just a light microscope image. Was one of the earlier works. By now, the quality and size of these flakes is further improved, yeah. But even here, it doesn't look so nice. But we had already quite nice homogeneous regions here where we have like very nice monolayers and sitting on the metasurface that we could study. All right, so we now implemented a variation of the nanocylinder diameter to sweep the, it was like a quadrupolar dominated resonance in the metasurface over the emission bandwidth of the MOS2. And we looked first at the PL microscopy, and the metasurface is always here in this, within these white dashed lines. And what we can immediately see is that the monolayers that are sitting on top of the metasurface are shining more brightly than those that are sitting on the substrate. You see this in all of these images. So we were quite happy, but we also found that yeah, that basically the photonic influence, like if this was really hitting a resonance or not, this emission in the metasurface was quite negligible, yeah. So there were mainly other factors like this freestanding nature of the monolayer on top of the nanodiscs, which contributed mostly to this enhanced emission as compared to the substrate. But where we saw a pronounced influence really from the photonic structure was in the emission, like in the directional emission properties. Here I show again these backfocal plane images now for a series of metasurfaces with different diameters. So what we do is we shift the resonance now from more or less off resonant into resonance with the emission of the MOS2, and we see that the more this is going into resonance, the more the light is directed from going sidewards to going upwards, like really out of the metasurface plane in this last image here. So what we learned here was that tailoring 2D TMD emission properties by engineering the combined photonic, electronic, and topographic environment is possible, but we really cannot concentrate only on the photonics. We also have to understand what's happening electronically and in the topography to understand all effects. So care must be taken when interpreting PL enhancement effects here, but we also conclude that the metasurfaces are very efficient in spatially tailoring the emission. All right, so this is sort of, we didn't use now many of the particular properties of the MOS2 apart from its strong bandgap fluorescence. So what is like a topic we are now really interested in is what I mentioned, to use this valley degree of freedom in tailoring emission properties. And here I showed two works from the literature where, for instance, separation of valley excitons in such a grooved metal film was shown, and also valley selective optical control in a dielectric metasurface. And so we're now interested in experimentally investigating a system which was originally proposed theoretically by Dragomir's group in Australia. So they had this, they had designed such a nano antenna. And if there is a chiral emitter situated in this antenna, it will direct light of different handedness into different directions. And so this is something that we wanted to, and we're actually collaborating now with Dragomir's group on this, but most experiments are performed now in Jena, so it's also Tobias working on this. So we basically have, so these gold nano antennas were fabricated in Australia, and we have put a WSE2 layer on top, which is resonant with this in its emission, with this wavelengths where this directional effect is expected. And we perform now measurements at 4 Kelvin, where the valley polarization from this WSE2 layer is quite pronounced. So we checked this, this is the fluorescence at low temperatures and also this degree of circular polarization. And now so this is ongoing work. We see first signatures now of this valley routing phenomenon. So this is basically the backfocal plane image where we look at the contrast of light emitted for left-handed circularly polarized or right-handed circularly polarized pump beam. And then we can look at the copolarized or cross-polarized output, and you see that this contrast changes now. We have something between, like, on the order of 10% changes how light of different handedness is now routed into different directions here. So hopefully we can conclude this work and show more details on this soon. And so stay tuned. There will be a publication hopefully soon. All right. So the road ahead for this is to enhance the complexity of spatial emission patterns, dynamic control of the emission properties. Also, we are interested in lasing phenomena in the future, thinking of electrical driving schemes, which should be well possible with these 2D materials, and also more fundamental studies for valleytronics. So we're just scratching the surface there at the moment. And if you're interested in light emitting metasurface in general, we made a big effort in writing a review together with Femius Kundering, in 2019, but there, we have also many of the basics, how this can be calculated and so on. All right, so, and one important step for our road ahead, where I will go a bit more in detail, is to have nanoscale site selectivity of 2D TMDs. In particular, for many directional phenomena, it matters where our emitter is located exactly in the nano architecture. Like, we don't want always the monolayer to be everywhere, but sometimes we just want in particular position of our structure. And therefore, we studied also nanostructuring of 2D TMDs. This was done by my former postdoc Rajesh. So he basically used focused ion beam milling in order to make both nano and microstructures out of these flakes. And he very thoroughly looked at how the properties then of the 2D TMDs are affected depending on the ion dose that's used for the milling. And here I showed just an atomic force microscopy image showing such a milled grating. So this has a you see here, this is nanometers. So we have something on the order of 100 nanometer stripes that have been milled there. And now we were looking at the photoluminescence properties of such structures. So here we have such a single crystalline monolayer. The pattern region you see is getting darker on the one hand because we are reducing the amount of material, but the decrease in photoluminescence is a bit more than what you would expect just from the fill factor, because there's also a slight damage due to the iron tails used during the milling. Yeah. But you see, we still have significant photoluminescence from there. It's just a bit less than what we get from the pristine flakes. And so smaller signal on the pattern flake, and we also looked at the spectra. So what we see there is a blue shift of the emission maximum with the iron dose, and Rajesh made a careful model and could mainly attribute this to the release of strain as the milling is performed. Like these CDD grown flakes, they are typically pre-strained on the substrate, and now this milling basically relieves some of this strain, and this leads to this blue shift. So, and we also checked again the valley polarization at low temperatures. And what we could, so here are some measurements at the bottom for the pristine flakes, and here for two different milling doses. So what we see is like there's the photoluminescence intensity for the different circular polarizations of the emission. We already see, so this peak here at the right hand side, this is just a substrate fluorescence, yeah, nothing changes here, but in this emission bandwidth of the MOS2, we see that the circular polarizations emit differently now, and using this formula you can then get the degree of the valley polarization, which is then plotted here now as a function of the ion fluence. And what we see is there is a slight decrease in the valley polarization, but if you look at the scale, yeah, so this is quite a zoom in already, so this is only a small, like the valley polarization is only slightly affected by the nano patterning. So it's really a good news, because it means that we can actually use this patterning method in order to place chiral emitters locally in our structures. All right, so this was the part I want to show on the photoluminescence part. Now I will also show something on the nonlinear metasurfaces. So like these, yes, questions?
May I ask a couple of questions,
please? Of course.
So the first one will be regarding the first structure with the MOS2. I'm wondering what was the initial spectrum and how did it change when after you transferred this flake on top of your metasurface?
Okay, yeah, we have measured this. I don't have the data here at hand now, but there is a very small shift happening, yeah. So because the MOS2 is just a monolayer, but it has quite a high refractive index, and you can basically sense the presence of the monolayer, but there is no fundamental big change in what you measure, yeah. So. And
did you have a resist above your cylinders, or you have put your flake above on top?
Yeah, so in the, I can maybe show this flip cut. So here, when this flip cut was performed, there was still the PMMA. Yeah, so this is needed for doing the transfer. We need something that carries this monolayer on top of the metasurface. But then the PMMA was removed, and we had just a freestanding monolayer on top of the. Yeah, so this image here on the right hand side, the PMMA is already removed, and it's just a MOS2 monolayer that's freely suspended on top of the discs.
So in our experiments, we suppose that we sometimes have a redshift of this exciton line due to sagging effects when you're putting on top of the metasurface.
Yeah, okay. So you're asking about a redshift of the metasurface resonant or a redshift of the MOS2?
Of the MOS2.
Yeah, okay. So there we saw quite some differences. Yeah, so we analyzed all the spectra, and we saw the spectra changed depending if the MOS2 flake was sitting, maybe I go here, like on the substrate area, or on the on this on the metasurface. And the main reason for this change, we attributed two detrimental effects from the substrate. So one is that the substrate dopes the monolayer, so we saw a shift towards the trion emission. Yeah. So it was not the pure excitonic emission, but a strong trion contribution for the MOS2 on the substrate. And also there is some like microscopic strain due to this, yeah, you can say like this surface is not perfectly smooth. So there will be like some, yeah, just some residual roughness of this glass slide, and the monolayer will sit on this and basically experience microscopic strain, which will also quench the photoluminescence to some degree, because yeah, some strain can lead to a transition to an indirect band gap locally also. So, but I think the main point was this doping and yeah, like depletion of the exciton peak towards the trion peak.
So, and regarding the second structure, you suppose that you have the strain again, release of the strain. So as far as I remember, when you have strain of the flake, you have the broadening, not only the redshift, but also the broadening of tail emission peak. So do you see narrowing after your FIB exposure?
Yeah, so this is now a bit hard to access. So here you see the spectra, and it's rather not like blue shifting, and also like I would say like broadening a bit, but we also introduce, as the ion fluence increases, we're increasing more and more damage. Yeah. So we cannot, like, it would not be a pure experiment to like look at straining properties here. Yeah. So yeah. So this is a bit difficult. Rajesh went through quite a complex model, yeah, to try and fit all these, yeah, all these points, like taking doping and strain and so on into account. But this damage is hard to account for, and this will also like at some stage the ion fluence is so high that you lose the peak. So we expect some broadening, and therefore we cannot analyze here the, yeah, basically the width of the peak. Just as a just as a consequence of strain or release of strain.
Yes. Thanks. Yes, it's now clear. Thank you for the answer. And another question from Maxim Gorlich.
Thank you, Anton. Hi, Isabelle, nice to see you. So I got a small comment just about the slide number 23, where you discuss this routing of circularly polarized emission from the quantum dot. So I don't know whether you're aware, so there was like a work from Sergei Tikhodeev group where they did basically very similar case. So they fabricated the structure with broken inversion symmetry. They put quantum dots in there, and due to this bianisotropic response, they routed emission. I guess the routing was like upwards or downwards, depending on the circular polarization. So I put the reference in the chat. It's like 6 years old or something. So the idea is very similar, because you break the inversion symmetry, and then due to that you route
so
emission.
I think what is maybe the difference is that, so it's clear if you have if you have some emitter there and this break of inversion symmetry. We actually also a couple of years already did something with quantum dots and splittering resonators when I was still in Australia, where we could also see this light routing effect. Yeah, but what we try to do now is we basically want to pump the system circularly polarized, so that we selectively populate only one of the K values. Yeah. And then you can, this is why you see then this valley polarization effect. So this is then preserved. You have then this exciton population that sits only in one of the K valleys, and preserves this information to a large degree. It's quite robust, and then decays again. And the circular polarization of the emission then still carries this information in which valley the excitons were sitting. So what the difference is basically where you put the polarizer, the circular polarizer. If you put this, like your quarter wave plate, if you put it in the excitation arm and populate an exciton population that only emits a certain amount of light and then goes in some direction, or if you put it in the detection arm. For detection arm, you can also use quantum dots, for instance, that don't preserve this valley polarization. Yeah. So so there we saw you could basically, it's more like a decomposition then into left-hand and right-hand circular polarization, and you can see such effects as well, just as a consequence of the break of inversion symmetry of your structure. but here we have this additional ingredient of the preserved valley polarization, and then we selectively want to couple this chiral emission that only goes in one direction in the first place towards a particular direction.
Right, I see, thank you. So, but I wonder whether you intentionally optimize these diagrams shown in the picture, or it's like just proof of principle that you route the emission into different directions and that's it.
Yeah, so this work here is not by us, yeah, so this is Dragomir's work. So they designed basically this structure considering a local chiral dipole. And for us, it's more like basic research at the moment to, yeah, like really altering the pump polarization and checking if we can see any of these valley routing effects for like having just a particular exciton population generated.
Thank you so
it's
much.
quite fundamental, and probably the structure is also not ideal for this, we figured out, but we see initial effects, yeah. So it's not as clear as in the original theoretical proposal for several reasons. So I mean, what we would ultimately like to work towards is if you would look at these images to basically just have red on the right, for instance, yeah, like everything going just in one direction, for instance, yeah, which you already can see in the intensity pattern. At the moment, we still have to do quite some data processing. You see, I'm showing this this contrast here in order to basically make some effects visible. Yeah. So we have not perfectly solved all this problem yet. Yeah. But I just want to try to explain what our motivation is, and that this is beyond like using quantum dots or other emitters, because we can really have this selective exciton population that we will try then to couple in combination with the inversion symmetry.
Good, thanks, Isabelle.
Okay.
Isabelle, before we proceed, I would say there's a comment in the chat from Dr. Ivan Shishkin. So he's noticing that you may probably consider using helium ion beam milling to reduce the damage instead of gallium ions.
Ah, okay, yeah, that's good comment. Yeah, so I was actually very skeptical to use gallium ions in the beginning. I wanted to use electron beam lithography, but Rajesh ultimately convinced me that yeah, if we use electron beam lithography, we always have to resist, and it's really hard to get rid of the resist in the end. Yeah, so if you make some small islands, and then you always have this resist sitting on top that you can't get rid of. Yeah, so and helium ion beam milling, I mean, there is a machine in Jena, but it's very hard for us to access. So it would be super interesting, I agree. So we had several ideas and proposals to use this, but we just can't really get hold of these people running this helium ion microscope. But I think also be super interesting to work with the helium ions, and could not only enhance resolution, but probably also quality further. And maybe one could look at introducing like consciously damaged, for instance, to have locally emitters, like quantum emitters sitting and so on. So there's a lot one could do there, but it's just a bit difficult for us to access. More practical problem, yeah. I
see. Thank you. I think we can proceed and maybe have a more detailed discussion in the end.
Okay, so I will try to speed up a little bit. So where was I? So maybe I will try to take maybe 5 minutes for nonlinearities and skip the rest, and we can rather have some discussion on this part or something. I
think we can have the last part as well. Since
okay, you tell me. Yeah. So let's see how we go with questions and so on. Yeah. Okay. So So for the nonlinear metasurfaces, it's also, I think, a good field of application to use them because of this resonant near field enhancement, and also these dielectric structures have relatively high damage thresholds compared to plasmonics. So we can actually pump them at significant levels and also theoretically describe them quite well. And now adding the 2D TMDs, we have also this strong Chi2 nonlinearity that enters the system. Yeah. And what kind of effects are we looking at? So one example would be Second-Harmonic Generation, just coming in with light at frequency omega. Then we have the metasurface, and part of the light will be converted into light at 2 omega. The real beauty of using metasurfaces for nonlinear frequency conversion is that they have sub-wavelength thickness, so we really don't have to worry at all about phase matching. And if you have ever worked in nonlinear optics, you know that phase matching can be very complex and also takes a lot of the energy that people dedicate to this kind of field. Yeah, every nonlinear optics book has a big chapter on phase matching, and here we just don't have to worry about it. So yeah, one system I'd like to show you is enhancing second harmonic generation in MOS2 monolayers. It's again collaboration with Thomas Perch and Frank Zetzfand's group. So, and also with Yuri Kivsha in Australia. So they provided us with these metasurfaces which sustain Fano resonances, or maybe some would call them imperfect or quasi bound states in the continuum. Yeah, and so basically what we were after were relatively high Q modes. And here you see the linear spectra of these structures. These are the experimentally measured ones for the two polarizations. So we find these two resonances with relatively high Q factor, and like one for each of the polarizations. And on the bottom is the matching numerical simulation. You see in numerics the peaks are quite a bit sharper, which is usually expected. And but in experiment we still have Q factors of about 250 for this first resonance and about 100 for the second resonance here. So we also looked at what really matters now for the second harmonic generation is the intensity enhancement for the parallel field components in the monolayer plane. And here I show a cut through the structure, basically in YZ direction, so like laterally, and then here what matters maybe more is the one here at the bottom, which is a cut in the XY direction in the plane where the monolayer is situated. And as I said, we look at the parallel field components of the pump that generate then the second harmonic. So we can see here a strong enhancement of the parallel field components in the relevant plane. And this is for these two resonances that are shown here. All right, so now we look at the second harmonic. Again, there is the experiment and the simulation. So, and what we find is, so this is the enhancement factor that we see here compared to an off-resonant structure. And so no detrimental substrate effects or so. It's really comparable, and we get about 35 factor of about 35 of enhancement in the second resonance, and something like 15 for this first resonance. In theory, it's first a bit more, but remember the Q factors were actually quite a bit higher. And also we have this laser, which has a certain pulse duration. So if we take all of these factors into account, we can actually get, so we're in the right order of magnitude with 35. So you see that taking the finite pulse width into account, like this Gaussian pulse, we already are at about 1000. And then considering that the Q factors are lower in experiment than theory, we end up really in this, we are expecting an enhancement value like this. We also checked the polarization sensitivity, so of the second harmonic, like on the degree, like the orientation of the fundamental harmonic that was incident for only MOS2 on glass. This is polarization independent, but for the metasurface at the two resonances, we see nicely reproduced that this this 810 resonance at 810 that's excited for X polarized excitation. This really produces also the second harmonic in X polarization, and for Y like for the second resonance, which was excited for Y polarization at 850 nanometer, we also have the second harmonic mainly showing for Y polarized excitation, and this is also in agreement with theory. All right, so this fits quite well. Here are also some images. This is a light microscope image. One can barely see the monolayers in this kind of setting. So what we actually compared was several regions on the substrate. We have, for instance, one monolayer here and one monolayer here. And we had both these resonant metasurfaces whose properties I showed, then also some non-resonant metasurfaces which did not show any resonances in the range of the pump. that we used, we had unstructured silicon and also regions of glass in between. And from the scan here, like spatial scan of the second harmonic, we could immediately see that the resonant metasurface and X-polarization is shown here. We had the most enhancement like really here on this resonant metasurface, and this is also made quantitative here on the right hand side, where yeah, we have the different polarizations and different wavelengths here, yeah, in these different colors. And then we compare unstructured silicon, non-resonant silicon, glass, and resonant silicon metasurface. And yeah, we see here, this was this highest enhancement that we see here for the bipolarization at 850 nanometer. Like some people compare with second harmonic on a silicon slab. You see, I think this is not really fair to do this. So there we get something like 3 orders of magnitude enhancement. This here is a logarithmic scale, but you see, like this is mainly quenched due to the absorption by the silicon. So I think one should compare ideally with the non-resonant metasurface, where the layer is also like freestanding, or maybe glass is also fine as a reference, but silicon I think is not a good reference. This sort of artificially boosts the enhancement value, but yeah, doesn't carry so much information. All right, so the largest second harmonic occurs for the metasurface for Y-polarized excitation at 850 nanometer wavelengths, and the second harmonic intensity enhancement of about 1,500 compared to unstructured silicon, but I said this is not so meaningful, and of about 35 compared to non-resonant wavelengths. So now let's understand a bit. So if I go back to these resonances here, we saw that this resonance at 810 nanometer actually had the higher Q factor than the one at 850 nanometer. So we were asking ourselves, why do we see now the larger enhancement for this second resonance here? And for this, it's really useful to look now at the field profiles, also at the second harmonic. So there the structure is off resonant, so I only show this at one wavelength here, yeah, for the 2 polarizations. And what we see is that, yeah, so the light is really, yeah, so the silicon mainly absorbs the second harmonic. So we see the most second harmonic field at this frequency in this plane where the monolayer sits, really in between the bars, yeah. So for Y polarization, like here in between, and for X polarization here in between the bars. So if you compare this now with the mode profiles of the excitation at the excitation frequency, we see like the higher Q resonance was this one here, but this one has barely any field in between the resonators, whereas the second mode is this one here, and here you see this has fundamental up to 50% of the total in-plane pump field is between the silicon bars for this resonance. So what we see is that, yeah, it's really important that we have an overlap of the pump field and the second harmonic field, and we have it in a region where the silicon is not absorbing light, yeah. So yeah, this really shows this important role of silicon absorption and spatial mode profiles at the pump wavelengths. And we can also say, I told you we don't have to worry about phase matching in metasurfaces, but we will have to worry about mode matching, as you see from this. But at least this is something that can be built into the structure and not something that you have to do by careful alignment later on in your optical setup. All right, so maybe one quick project also on the SHG, which uses also nano patterning, so bringing all of this together. To have site selective second harmonic generation. So again, we use this focused ion beam milling approach now to make basically such grating structures. So it's more like a micro patterning now. So we can see this in the light microscope image in this case. And here's also just the second harmonic from this pattern monolayer. You see, similar to the photoluminescence, the second harmonic is decreased in this milled area, but it's yeah, it's still present. We can still study it, yeah. And yeah, so what we did then is first we just milled such a grating with a 675 nanometer grating period. And since the excitation was at 840 nanometer, this is basically like a sub-wavelength structure at the excitation. So a non-diffractive structure at that excitation, but here's a close-up of the structure, but in the second harmonic, this becomes a diffractive structure, and we basically start seeing diffraction orders here in this backfocal plane of the second harmonic emission. Okay, so and what we can do now is basically use ideas from amplitude holography. And for instance, what's quite well known, that vortex beams can be generated by such a grating like such a fork grating like structure. So we milled such a fork grating. You see here there is this this fork-like structure here in the center. I hope you can see it. And if we now do the same experiments, then we're actually generating vortex beams in the first and second diffraction order for the second harmonic. So this is, you can consider this like a ultra thin metasurface sitting on a substrate, like just one molecular layer thick, but it's able to do beam shaping action on the first diffraction orders. All right, so yeah, this was basically what I want to show about nonlinearity. I think we are sort of running out of time. Maybe I can very quickly show, like just go through this. So often the metasurface is like considered like a sheet of nanoscale thickness. I also used these words in the beginning, yeah. And now one idea we had also for the 2D materials is to get rid of the substrate and use a 2D material as substrate. And yeah, I'm just citing here also work by Stefan Linden, where they had used some carbon film and milled some holes in this to make some like inverse, like Babinet type metasurface. And our idea was to use carbon nanomembranes also from our collaborator Andre Truchani in Jena as substrates and really put plasmonic meta-atoms on top. So here's the schematic. This is Denizan who did this work. It's of course largely not to scale, yeah. So we will have this 1 nanometer thick substrate and typical splittering resonator surfaces on top. And yeah, we basically devised this fabrication procedure. This carbon nanomembrane is something like it will create like really something that's effectively a freestanding metasurface because it doesn't interact. We cannot show that it interacts with light in a measurable way, yeah. And yeah, so we made basically these structures situated here freestanding on top of a TEM membrane, and there are some zoom ins, yeah, of the splittering resonator, so a rolled up structure that was ruptured. Yeah, and then we can measure also the optical response, and it looks really very much like a freestanding splittering resonator metasurface. So maybe I can stop here. We wrote also a review on combining 2D materials with mirror resonant structures, so not so much the plasmonics. And I think what's the outlook for this research direction is to also include this active tunability, which the 2D materials provide and which could be leveraged using the nanostructures to really look at tailored nonlinear and quantum systems, engineer not only the nanostructure but also the TMD, so this can be grown and there's still room for material development there. And then like using also these freestanding structures, we could think of incorporating metasurface also in Van der Waals heterostructures, creating stacked metasystems, and I think there's a lot that could be investigated there. And I think it's now lunchtime in Russia, right? So like in St. Petersburg, so maybe I make you all hungry now with this image. And I think I'm going to stop here, and the last topic is anyway a bit off topic, so I don't have to show this. And so I jump to my, if I'm allowed to, I would jump to my last slide. Is this working? Yeah, so just to thank the current team and funding. This is the current team, the funding agencies. I thank you for your attention and again for the kind invitation. And I want to use the opportunity also to say that we have open PhD positions. So in particular, we recently, like very recently, got a big graduate school funded together with Australian National University, which will educate in total something like 40 PhD students on active metasurfaces. And all the students have the opportunity to, or are basically expected to gain a dual PhD degree from FSU, so Friedrich-Schiller-University in Jena and Australian National University. I hope it's not inadequate to advertise this, and maybe it can be interesting for some people. The job ad is not out there yet, but if you're interested, just contact me. So it starts officially on 1st of January, but they will also be hirings later on, like 1.5 years later, and we are basically also able to hire right away for this. Okay, thank you very much.
Yeah, thank you, Isabelle. It's quite timely to advertise this. It's a very nice place for that, I think. So thank again for your brilliant talk and for accepting our invitation. So we have some time. So the lunch time will be in a couple of hours in St. Petersburg. So for this reason, I think we have some time for questions. As I don't see any from the audience yet, I would like to ask you regarding the part of second harmonic generation from the TMD based so integrated metasurfaces with TMDs. I'm wondering, so you have here, you have some frequencies that do not match, so both the resonant frequencies of the metasurface and the frequency of your second harmonic, which coincide, and they do not match the exciton frequency of TMD. I'm wondering, so of course the TMD doesn't have much second harmonic signal out of exciton resonance, but I wonder if this system would work even better if you match your resonant frequency of the metasurface with that of the exciton response of TMD.
Yeah, that's an excellent question. So in principle, this this nonlinear susceptibility of the TMD shows several peaks. Yeah, so it's strongly wavelengths dependent, as you say, and the exciton frequencies are certainly so Chi2 will be enhanced there, but we are also working in a sweet spot. Namely, we are working in this so-called C peak, which is the band nesting region of the TMD, where the Chi2 is also enhanced, yeah. And the reason why we're working there is basically our excitation laser, yeah, which is a little bit tunable, so we can make this kind of second harmonic spectroscopy, but we can't tune it to work at the exciton wavelengths. But as I said, it's also a region where the monolayer shows a strong second harmonic, which is also you always see the C peak, which is also like giving strong enhancement of the I think I have this. Do I have this? Let me see. I have to check. When I introduced the 2D materials, I don't exactly remember which image I'm showing. Yeah, this one here. So, okay, let me think. This is not our work, so I have to go into this. But this shows basically we have the. Yeah, so there's this A peak, B peak, and then this band nesting region, yeah, this C peak. So you see it's also like a sweet spot for working with second harmonic there, yeah.
Yeah, but still, if you have a titanium sapphire laser, you can use molybdenum diselenide, which is...
Yeah, so we have this available now, yeah. But at the time when we were starting this project, the collaborators could only grow the MOS2. So yeah, but now I agree we could also work in the exciton range, and this would be nice also like for tuning, for instance. Yeah, so this strong tuning of second harmonic, I think this was mainly shown at the exciton frequencies. Yeah, I think that I'm not so sure how tunable the C region would be. Yeah.
You mean the electric gating?
Yeah, by gating. So tuning the second harmonic by gating. This is, I think, also in this work here. This shows is it this one? Oh, I don't want to say something wrong now. Yeah. So there was this this work which showed tuning of the second harmonic as a function of applied gate voltage. I think it's also in this work that I show here, but I'm not 100% sure at the moment. Yeah, but it was definitely shown.
Just the photoluminescence, I think, yeah.
Okay, then it's a different work, but if you're interested, I can send you the work, but I don't have the reference in here now, so I have to check it again. But it was demonstrated.
It would be nice. I just emailed you right before the seminar with this correct. Okay. So, colleagues, do we have any other questions?
Yes, sorry, Anton. Thanks a lot, Professor Staude. So just maybe a general question, since I don't work with neither 2D materials, neither with metasurface. I wonder, do you use metasurfaces for guiding the emission from 2D materials? And the second part of the question is, how many periods of metasurface do you need covered with with your TMDC to call this part which is covered with TMDC a metasurface, like 10 to 20 or 30? Since I think regarding, I mean, yeah, depending on the amount of periods which are covered with TMDC, there should be some differences. I think it's a lot.
Yeah, so the first question was if we are directing the light using the metasurface, or so this is what I showed basically in this first work, but we also showed this for many other types of emitters. this is what I basically showed here, where we use typically this backfocal plane imaging, and then we can design the metasurface in a way. So I didn't show many details there, yeah, but there is a condition which is called the surface lattice resonance condition, where basically you hit where the wavelengths that you're emitting corresponds to the lattice constant, but to the wavelengths of the material typically in the substrate of the metasurface. This is sort of many details now, but you have a condition there where with normally incident light you can excite highly resonant mode in the metasurface, where you don't only hit these mirror resonances, but where they are strongly interacting in the metasurface and basically forming an extended mode. And vice versa. So since you can excite this by reciprocity, so if you can excite it with a normally incident beam, you can also do it the other way around. If you have emission happening at a frequency that hits the surface lattice resonance condition, by reciprocity, the light will be channeled normally out of the substrate plane. And what I described now qualitatively, we can also calculate. I didn't go much into detail of calculations, but if you design these patterns, you can basically use the reciprocity principle. You just calculate absorption or even local near fields in the metasurface as a function of incident light, so of plane wave excitation from different angles, and you sweep all the angles and you see how the metasurface is excited, and then you apply the reciprocity principle to reconstruct the emission pattern. So this is how this can be designed. So typically one has some heuristics, like knowing of the existence of surface lattice resonance or of whatever causes like a deflection of a beam or so, and then this can be used to really design and to check this. The second question, okay, how large does the metasurface have to be? I mean, for the metasurfaces themselves.
I mean, sorry, not the metasurface. So when you cover your metasurface partially with TMD material, TMDC material, so how much area should be covered with TMDC to call this part of the metasurface, well, to make this metasurface part work as metasurface? I mean, 10, 20,
okay, I understand. Okay, maybe a few points for that. Like the first one is like these flakes. You see, they are on the order of several tens of micrometers by now, even hundreds of micrometers, because the growth has also progressed a lot. So there we're really it's I don't think it has to be questioned that much if we have these kind of sizes. It depends also a bit on the type of resonances. Yeah, if we have something that is really a delocalized mode, like for what I showed in the nonlinear project, we had really this Fano resonant or BIC type state, which is really strongly delocalized, uses delocalization to enhance the Q factor, and so there. The metasurface, whatever you define now as the metasurface, should have a certain size. So people have shown that the Q factors decrease at a certain point if you make the metasurface smaller, because you cannot delocalize so much anymore. Yeah. So, but this is just the metasurface. The question is then also like, how big should the TMD be? And as I said, the influence of the TMD on, I mean, I think I even had this shown for the nonlinearities, if I can find this quickly. So in theory, look, we basically also incorporated the monolayer, and you saw that this leads to a small redshift, yeah. So it's similar to what we see in experiment as well, and so what you would have is like a locally slightly detuned resonance, yeah. So but it's a small shift, and if you don't have that sharp resonances, and you see already in experiment they are not as sharp, yeah. So if there's a small shift, this will not strongly alter your mode properties, and I think the effect is sort of small, yeah. So you can still, even if your TMD is not covering the whole metasurface, it doesn't have a, like, we didn't experience any problem with that. Yeah.
Yeah, sure. Thanks a lot. And sorry, one final question. So regarding the experimental part, so should I excite my metasurface with TMDC with like a large beam, or I can excite it with localized, I don't know, like with the diffraction limit size, very sharply focused beam to
it depends what you want to show. Yeah. So so for these for these type of metasurfaces that I showed here, I think the spot size was covering like a few lattice constants. But then, like, if you think now about, like, maybe I can show this example here again, like this work here goes already more in this direction of nonlinear wavefront control, yeah. And there's nicer to have a slightly more extended spot, yeah, so that you, like, here is still a simple structure. If you have a few micron, it's fine, yeah, you focus this on this fork structure and it works. But think of making a nonlinear hologram, for instance. This will have a certain extent, and then of course you have to spread your beam to, yeah, basically interrogate a significant fraction of this extended holographic structure. So there's no, yeah, no clear you should do this or this. It really depends on what you want to show. And yeah, like expanding the beam a little bit, you typically if you don't have any requirement there, is if you have a very small spot, you also only generate second harmonic in a very small area, and therefore you have a smaller signal, right? Because you cannot crank up the power infinitely. At some stage you would destroy the structure. So it's usually nice to have a slightly, like, not the sharpest focus you can do. It's probably not the best working condition. And yeah, in addition, yeah.
Yeah, thank you very much. Thanks a lot. And once again, thank you very much for very impressive results.
Oh,
very inspiring.
My pleasure. Thanks for the questions.
If you don't mind, we have another Misha, please, very short question from Mikhail Rybin.
Okay, Isabelle, thank you very much for your terrific presentation. As usual, it was very brilliant. I wonder about coherence of photoluminescence. When we generate second harmonic, is this coherent? But is it possible to generate photoluminescence with some coherent properties from the samples?
Yeah, that's an excellent question. We were also asking this ourselves quite a lot. Yeah, so yeah, you're exactly right. Yeah, so in second harmonics, things like wavefront shaping are actually much easier than for photoluminescence, because you are in the coherent regime. For PL, I mean, or emission generally, I think, like, you can use some mechanisms to establish some partial coherence. And I'm like not a theoretician who could really go into the details of coherence theory now, yeah. But like, there were works, for instance, by John Schuller, who used who established who did some, like, spatially variant metasurfaces for emission, and was able to direct the light, for instance, based on, like, confining the light in a quantum well. Thereby, at least you have the K vectors, like, confined to those that were propagating in this well, and you had sort of a good condition for shaping again. Maybe not as good as, like, a coherent incident wave, but you had some partial, like, you had some control, yeah, for the input light field. Generally, also the coupling of the resonators can establish some coherence, yeah. If you even have, like, one emitter which excites first one of the disks, this one excites then neighboring disks, and like, for a single emission event, this interaction between neighboring resonators can also be coherent, right? Because this is like coupling of a particular, like, event of emission. And finally, maybe to mention, it's also part of why we're interested in lasing. So I think lasing would also be very interesting as a mechanism to establish coherence, or maybe some predecessors of lasing to at least have some partial coherence established. So that's my thoughts on this, yeah. So one can learn maybe also from the community working with thermal emission from metamaterials, where they also showed that the coherence of the emission could be improved by the structuring and by emitting into particular spatial modes, for instance.
Okay, thank you very much.
Thank you, Misha. Thank you, Isabelle. So I see that we don't have any more questions, at least for this formal part. So Isabelle, I would like to thank you again for a brilliant seminar. So it's always very nice to listen to you, and very interesting topics.
Yeah, thank you for the invitation. It's always a pleasure to meet you all, and yeah, keep up our yeah, and maybe we can intensify collaborations in the future. I mean, Artyom will come to Germany soon, right? Hi, Artyom. Yeah. So yeah.
Hello.
Yeah. I think we can intensify, especially in the field of 2D materials, for instance. So, if you don't mind, I will briefly announce the seminar. The next one, we have a very special seminar next time. So that will be given by Dr. Artem Danilov from the Atacube Systems company, the NeoSpec product line, and he will be making an overview of applications of scattering, scanning, near-field optical microscopy and spectroscopy. That will be very useful for theoreticians and students and for everyone. So keep updated and stay safe, and good luck to everyone. Thank you for joining the seminar.
Bye, thank you.
Goodbye.